Alright, so we are talking about rates of change and its application to physics. Before we start, you have to know that the average rate of change is the change over a given distance on a function. So for example, if you have this function, then the average rate of change between here and here is this slope. And that slope is the rate of change in between these 2 points. The instantaneous rate of change is the slope of a tangent line to a single point. So for example, if you have about the same graph, close enough, then the slope of this point is about there, and the slope of this point is about that. And so the instant rate of change is at a certain point, and the average rate of change is over a certain area. Hopefully that's review. In some problems, you won't have enough information to get the instantaneous rate of change, so you'll just have to make do with an average rate. For example, you'll have a table of say 1, 2, 3, 4, and 5 seconds, and you'll have positions, places where whatever you're looking for is, say 2, 5, 7, 1, 3. If you're looking for the instantaneous rate of change at 3.5, you won't be able to find it because there's nothing in between 3 and 4. So you'll just have to take the average rate of change between these 2 points. And now we're going to show you an example.
Alright, so now we're going to show you a problem that was previously mentioned before. This example, Diddy Kong has been recorded distances he traveled at certain instances of time, minutes, while driving on Mopac one Sunday. How fast in miles per hour was Diddy Kong driving at time 22 minutes? Alright, so we have the table here, and it wants us to find how fast he was traveling at 22 minutes. And if we look, we see that 22 minutes is 1 hour over 60 minutes. So roughly equals 0.367 hours. This value is the value in between 20 minutes and 25 minutes. We're at 0.33 is 0.417. So what we need to do is we need to find the slope between these 2 points. So what we do is we have miles per hour, so we have the 19.7 minus 15.5 divided by the 0.417 minus 0.33. This gives us an estimation of like 50 miles per hour. That's your rate of change for that one.
Go. Alright, so one of the nice things about math is that you can actually apply it to things like physics. And in physics, you have the position of a particle, or an object, or whatever you're talking about, and that's generally said as S equals a function of time. You also have velocity, and the velocity is the instantaneous change of the particle's position. And this is that V equals S prime equals F prime of t. And in addition to velocity, you have acceleration. And acceleration is to velocity what velocity is to position. Is that spelled right?
Psh, this isn't English.
That is true. That's good enough. And so the acceleration is V prime or S double prime or F double prime of t. And above acceleration you have other things like jerk, but those don't matter right now. And so for position, what you're going to be solving for is the displacement, which is the change from the change in s, the change in position. Velocity equals the displacement over the change in time. Now this is the definition of average velocity, instantaneous and average. And the same thing for acceleration. You have the change in velocity over the change in time. What else do we need to talk about?
So now we're going to look at another problem, and this one is a dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second, and the problem is modeled by this equation right here. So if we graph the graph, we see that it's like an upside down parabola, and that at 5 seconds, this velocity line goes from positive to negative, so which tells us that our turning point is right at 5 seconds. And at 5 seconds, we can see that the tangent line is equal to 0. And so if we plug in 5 seconds into the original equation, we see that 160 times 5 minus 16 times 5 squared equals 400. So our total height is 400 feet for how high the rock reaches. Go.
Part B, what is the velocity when the rock is 256 feet above the ground on the way up and on the way down? First, you have to solve for the time when the height is 256. Factor this out and you'll find that the time is 2 and 8 seconds. 2 for the way up, 8 for the way down. Now you find the derivative, the velocity. This should be summed up very clearly in another video, but the first derivative is 160 minus 32t. Plug in 2 for t and you get 96. Plug in 8 for t and you get negative 96. So this is the velocity on the way up, and this is the velocity on the way down. Go.
Alright, so now we're going to find the acceleration of the rock at time t during its flight. So s of t equals, this is the original equation. Now if we find the derivative of the original equation, we get the 160 minus 32t. Now if we find the derivative of that derivative, which is the second derivative of the first equation, then we find that the value of the acceleration is negative 32 feet per second squared at time t during the flight. Go.
Alright, part D, when does the rock hit the ground?
Go.
Part D, when does the rock hit the ground? Well, you're looking for the displacement of 0 because the height of the ground is 0. So you take 160t minus 16t squared, factor it, you'll find that 16t times 10 minus t equals 0. Well, when t equals 0, obviously the height equals 0 because you multiply the whole thing by 0. Also, when t equals 10, you multiply this, or this becomes 0, so you multiply everything by 0, so it becomes 0. So the rock hits the ground again at t equals 10 seconds.